Thank you for your interest in our technical presentation from the 2022 Sink or Swim Conference. My name is Mark Langell, and I'm a customer application specialist at ANGUS Chemical Company. And today I'm going to be talking about pigment dispersions and how amino alcohols can be a very helpful formulating tool for dispersing and stabilizing a variety of different pigments. The use of pigments is ubiquitous in coatings, and this is the case because they perform a multitude of functions within a coating formulation. Aesthetics usually comes to mind first, but in addition to color, they can also affect gloss and even the physical feel of a coating. Pigments and inorganic extenders are also critical when it comes to paint performance, where they can heavily influence the mechanical and resistance properties of a coating. There's also pigments that can provide direct functional performance properties, such as corrosion protection, either through the use of anti-corrosive pigments or by the selection of extenders that have plate-like morphology that helps to control the transport of water, or rather inhibit the transport of water through a coating. So while pigments are critical to formulations, they can still present an array of challenges. And many of these challenges arise from the need to balance both wet and dry film properties. On the one hand, you need to make sure your pigments are well dispersed and stabilized so that you can have a reasonably stable formulation. But you're also concerned with other application properties like sag and leveling, which are highly influenced by pigment choice. On the other hand, you need dry film properties that meet all of the protection requirements of the coating. That includes the right gloss and color and various resistance properties. And most typically, unfortunately, it's the case that most formulation strategies that are good for wet paint properties may not necessarily be beneficial for dry film properties, or vice versa. One of the first steps you can take to try and balance the wet and dry film performance needs in a formulation is to maximize the effectiveness of the pigments that you're using. Pigments need to be of a certain size to be stable in the wet state and also to perform as you expect them in a dry state. Most dry pigments are composed of agglomerates, which arises from the manufacturing process of these materials, where multiple primary particles end up being stuck together to one another. You need to mix these pigments and introduce enough energy to the system to break these agglomerates up. You can measure how effectively you've done this by particle size measurements, which is illustrated on the right of this slide. The gray line represents a poorly dispersed set of pigments that consists of a large fraction of larger particles and agglomerates. But as you better disperse those pigments, you can achieve the dark blue line, where you have a smaller distribution of particles that has a smaller average particle size. And this is really the ideal scenario. But there's challenges from getting from that gray line to that blue line. And the first is simply dispersing pigments and breaking up the agglomerates. But then the second critical piece is that you need to properly stabilize those pigments so that they don't revert back to their original agglomerated state. Formulators have many tools at their disposal to help disperse and stabilize pigments. The most commonly used are dispersants and surfactants. And in either case, they consist of pigment affinity groups, oftentimes carboxylic acids, that will interact with pigment surfaces, and then a polymer or an oligomer portion that interacts less with the pigment surface provides a steric stabilization to prevent reagglomeration from occurring. There are other tools as well, such as rheology modifiers that can be used to adjust the energy transfer from a dispersing blade to the pigment particles. In other words, a higher viscosity grind is typically more efficient at dispersing pigment particles. There's also a host of tools and equipment that can also help. However, some of these additives, I should say, can come with negative effects. And so that's why you usually need to use defoamers to counteract some of the negative effects of either the equipment you're using or some of the dispersants and surfactants that are necessary to disperse those particles. In general, higher use levels of these additives like surfactants and dispersants can often help improve your wet paint properties, but they can also have a negative influence on the dry film coating performance. So you always have to keep in mind that balance when you're trying to optimize a formulation. There is, however, another tool to disperse and stabilize pigments that's often overlooked by a lot of formulators, and that's amino alcohols, which act primarily by electrostatic stabilization. And this isn't unfamiliar to most formulators. So most traditional dispersants are composed of either carboxylic acids or phosphate groups which can stabilize pigments by, in part, electrostatic interactions. You can also achieve electrostatic stabilization using inorganic bases or ammonia, for instance, but amino alcohols are particularly effective tools at this. Really why they're so effective is because they're so efficient at dispersing pigments, and I'll show you lots of data around this. But they can also partially or completely replace some surfactants and traditional dispersants that are used. They can also have compatibility with zero or low VOC formulations. And if you choose the right amino alcohol, they can also have favorable odor or EH&S profiles. So I mentioned dispersant efficiency, and one way that you can measure efficiency of a dispersant is through dispersant demand curves. In these types of measurements, you titrate in a dispersant, either a traditional polymeric type dispersant or an amino alcohol, and you measure the viscosity of a pigment grind as a function of the dispersant concentration. Before you've added sufficient dispersant, you have a thick paste, which is kind of shown in that photograph on the far left. But after you've added a sufficient amount of dispersant, the viscosity of the grind will drop pretty dramatically to create a low viscosity, easily pourable slurry. And the amount of dispersant that's required to see that viscosity drop reflects the efficiency. So on the graph on the right, you can see two dispersant demand curves for titanium dioxide. One is for an amino alcohol, which is the dark blue, and the other is for a polymeric type dispersant, which is the light gray. The viscosity drops off at a much lower addition rate of the amino alcohol than it does for a polymeric dispersant. So in other words, you need significantly less of an amino alcohol than you would a normal polymeric dispersant to achieve a similar quality pigment grind. However, it's very important to keep in mind that just like not all polymeric dispersants are created equal, neither are amino alcohol dispersants. And so shown on this graph is a titanium dioxide dispersant demand curve for the polymeric dispersant versus 3 different amino alcohols. We have triethanolamine in dark blue, diethanolamine, which is in green, and aminomethylpropanol, which is in yellow. So when you look at these curves, triethanolamine, it really lacks the ability to effectively disperse pigments, while diethanolamine shows some desirable performance, but it's not nearly the efficiency of the polymeric dispersant. And so of this set, the aminomethylpropanol has far and away the most effective pigment dispersion properties. You could look at this and you could argue that perhaps it's molecular weight that's a big factor here, because the highest molecular weight amino alcohol is the least efficient, while the lowest molecular weight amino alcohol is the most efficient. But we know from a lot of experience that it's actually quite a bit more complicated than that. We've looked at the performance of various amino alcohol structures, and even among structural isomers of amino alcohols, there are noticeable differences in efficiency when it comes to dispersing pigments. So to illustrate this, there are a number of dispersant demand curves on the plot on the left. The solid yellow line data is for aminomethylpropanol, while the solid blue line data is for DMAMP, which is the dimethyl version of AMP. I can show you the specific chemical structures of these two materials because they are commercially available, but we went and we synthesized structural isomers of these two materials, which are the corresponding dashed data points. Structural isomer means that the molecule has the same molecular formula, but a different structure. So just imagine that we made a slight rearrangement to either the methyl or the hydroxyl groups on the molecules that are shown. But what we find is that neither of the structural isomers are as effective as their respective commercial products. So small differences in chemical structure do make a big difference in how effectively pigments can be dispersed. Not all amino alcohols are equally effective at doing this. But from this data, you can see why we focus so much of our effort and work on AMP. And that's because it is a uniquely effective amino alcohol for dispersing pigments. We also know that AMP is not only effective with titanium dioxide. Particularly in architectural coatings, there are many different extenders and fillers that can often be used. And we look at the effectiveness of AMP to disperse different inorganics, and some of that data is shown on the graph on the left. So this is not a dispersant demand curve, as I previously showed, but an adsorption curve, where for a given concentration of AMP that's in solution, which is plotted on the x-axis, we can measure the amount of AMP that is adsorbed onto the pigment surface, which is plotted on the y-axis. There's usually a very strong correlation between adsorption of a dispersant to pigment surfaces and the ability of that dispersant to properly disperse and stabilize the pigments. What we find is that we get the highest adsorption of AMP onto extenders, such as a number of clays and titanium dioxide, which is the data in red. Adsorption onto calcium carbonate, on the other hand, is a bit less. And so our understanding of this behavior is that the amine group that's on AMP is primarily responsible for interacting with negative charges that are on the surface of the pigments in extenders. So the greater the negative surface charge on the pigment surface, the more AMP has an opportunity to adsorb to that surface. We have done a significant amount of work over the years in both architectural and waterborne industrial coatings, and we have a fairly good understanding of how to optimize formulations, primarily based on titanium dioxide with amino alkyl dispersants. And the typical formulation strategy is to use a low level of amino alcohol. This is typically between 0.1 and 0.25% on total formulation weight in the pigment grind, and use that as a replacement for 30 to 50% of the primary dispersant that's in the formulation. This can yield improvements to both the wet and the dry film properties. So in the case of an acrylic DTM formulation shown here, we're able to improve the viscosity stability of the formulation, meaning that we're able to better stabilize the pigments. But we also improved a number of dry film properties. Of particular importance, we could improve the hiding and the gloss of the formulation, two properties that are highly dependent on the quality of the pigment dispersion. We could also improve other properties like water resistance and corrosion resistance. Because we're able to create a coating with better barrier properties, in part due to achieving a better distribution of pigments through the film, but also in part due to the reduced level of polymeric dispersant that's now in the formulation. And so by minimizing the total amount of water-sensitive species in the formulation, we can help to create a more hydrophobic coating that better resists water and salt penetration, for instance. However, pigment chemistry can be very diverse, and there's plenty of other pigments that are not titanium dioxide. But even within titanium dioxide, the surface chemistry can be highly variable due to different treatments of alumina, silica, or zirconium oxide onto the surface, which can greatly change the surface chemistry of different grades of commercial titanium dioxide. But when you start to look at other pigments, it becomes even more complicated. So if you take carbon black, for instance, which is generally a very hydrophobic surface, but you can have various chemical functionalities on that surface. Commonly, you might find carboxylic acid groups to help aid in the dispersion of that material. In the case of organic pigments, the chemistry of these materials can be even more variable. So for instance, the structure of pigment red 122 and pigment blue 15.3 are shown on the far right. Many organic pigments are also quite hydrophobic, just like the carbon black, and it makes them particularly difficult to disperse and stabilize. And so we know that AMP is a great dispersant for titanium dioxide and many extenders. We've recently done some more work with carbon black and organic pigments and found that AMP can also help to disperse and stabilize these other types of chemistries as well. We evaluated the ability of AMP to disperse carbon black in a flexographic ink formulation. If you're unfamiliar with the process of making a flexographic ink, there are two places in the formulation where an amino alcohol can be introduced. So the first is in the resin solubilization process, where a base is required to neutralize the acid groups on the resin. The resin solution is then introduced into the pigment grinding step, and this creates a pigment paste. This is when something like AMP has an opportunity to interact with and help disperse the carbon black particles. The finished ink is then completed from the resin-containing pigment paste, and the final pH can be adjusted with a neutralizer. Again, we are looking at the neutralization of this with AMP. So in our studies, we are comparing the use of AMP to ammonia, and this is both in the resin solubilization step and also in the final pH adjustment step. What we found is that AMP can help to more quickly disperse carbon black. We monitored that by particle size measurements after 10, 30, 60, and 120 minutes of grinding. If you look at the graph on the left, this is the particle size progression of the AMP containing ink. And you notice that the peaks on the far right, which correspond to large carbon black agglomerates, are decreasing with time. And so if you then compare that to the graph on the right, This is the ammonia-containing ink, and the particle size reduction occurs much more slowly. There's even a fairly significant difference, even just within the initial 10 minutes of grinding, where AMP is showing a much quicker decrease in the number of agglomerates that are seen. The other benefit of AMP we found was around dispersion stability. The initial particle size measurements for both the AMP and ammonia-containing paste are shown on the graph on the left, with AMP having a lower number of overall agglomerated carbon black particles. That's the data in red. However, we took these initial pigment pastes and ran a storage stability test for 10 days at ambient conditions. And we found that while both samples showed an increase in the fraction of agglomerated particles, the ammonia-containing pigment paste had a noticeably higher number of agglomerates. So AMP is helping to not only more quickly disperse the carbon black, but it's also better stabilizing the carbon black and preventing reagglomeration. As previously mentioned, it's important that you achieve a balance of both your wet and your dry film properties. When we screened a few of the critical properties of the finished ink, we found that AMP created a darker black. So in other words, improved jetness, and also higher gloss. Both of these properties are an indicator for an improvement in dispersion of the carbon black within the ink. You can also see from the photographs of drawdowns that the reflected image quality and the distinctiveness of image are both improved with AMP. This is a very interesting result because carbon black is a much different type of pigment than titanium dioxide, yet we still see benefits for using AMP to help disperse that kind of pigment, and at least in this case, in an ink application. So we were very interested, based on those results, to see what other types of pigments AMP might help disperse and stabilize. So we took a look at select organic pigments. As a simple starting point for screening, we looked at the absorption of AMP onto pigment particle surfaces. Just as a point of reference, with a low level of AMP in solution, in the case of titanium dioxide, we can see upwards of 80% of AMP that's absorbed onto the pigment surface. We also see very high AMP absorption onto copper phthalocyanine blue, which is that structure shown on the top right, where we actually are above 90% absorption when the concentration of AMP is 1% or less in solution. Other pigments, like pigment violet 23, still show absorption, but it's not as great as the blue pigment. So in that case, with the pigment violet 23, we're getting around a 43% absorption, and that was when 0.5% of AMP was in solution. But these results indicate that you can still get fairly good absorption of AMP onto organic pigment surfaces, which is a good sign for being able to disperse and stabilize those organic pigments in solution. To study this further, we worked with a starting point water-based pigment paste formulation for pigment red 122, which is quinacridone red, which is actually a bright pink color. Our starting point formulation contained a dispersing agent. This was a commercial dispersing agent that was a combination of non-ionic and anionic surface active compounds. And then we took this formulation and created an AMP containing version. And we did this by removing 50% of the existing dispersant and replaced it with AMP. So one change we immediately noticed was that the viscosity of this new AMP containing pigment dispersion was significantly lower than control. So we increased the pigment solids to match the control, and we found that we could increase the amount of PR122 in the paste by 50%, while still not exceeding the viscosity of the original control formulation. So already from these results, we are seeing that AMP is allowing us to create a much higher solids pigment paste than we would have been able to create otherwise. So to confirm some of our initial observations, we also looked at particle size of these two pigment pastes. They were both prepared using identical protocols, using grinding media in a speed mixer. And we found that the particle size analysis confirmed our initial belief that AMP can yield smaller particle size pigments, which is the data in blue as compared to the control pigment paste, which is in green, which has a larger average particle size. We also looked at both the reproducibility and stability of these PR122 pigment pastes. We made 2 batches from scratch of each pigment paste and measured particle size, which is shown in the blue and green data for the control paste at the top and the AMP paste at the bottom. And the reproducibility is quite good, where we're consistently seeing a lower average particle size when we formulate with AMP. We then took one of the batches and heat aged it for 45 days at 45 degrees Celsius and remeasured the particle size, which is the data in red. The AMP containing paste is really extremely stable, where we only see a very slight decrease in the occurrence of the smaller particles. Comparatively, the decreased count of primary particles in the control pigment paste is much greater. So we're seeing much better stability when we're formulating with AMP. And finally, we wanted to evaluate the effectiveness of these 2 different pigment pastes in white base paints. So we selected 8 commercial white paints and tinted them with the 2 pigment pastes. We looked at differences in color strength of the AMP paste compared to the control. What we find is that although there are some variability in performance between the different base paints, 7 of the 8 showed improvements to color strength with AMP, which is the data in the dark blue bars. We found that the color strength was the worst in a bio-based alkyd paint, but in the other paints, which ranged from synthetic silicate blends to acrylics to urethane alkyd blends, that we were getting between a 2 to 6% improvement in color strength. And this improvement becomes even more clear in aged pigment paste. So we repeated this experiment again, but rather than the fresh pigment paste, we used samples that had been aged for 28 days at 45 degrees Celsius. And that data is plotted as the gray bars. We find that for the majority of the paints, the color strength of the AMP paste shows an even greater magnitude of difference from the control paste. And what is somewhat hidden within this data is that the greater color strength comes primarily from the loss of color strength from the control formulation as compared to the more stable AMP containing pigment paste. So to draw some conclusions from these recent studies of ours, we've learned that in addition to titanium dioxide, AMP can be a highly effective dispersant for carbon black and also organic pigments. Amino alcohols can be a very effective formulating tool for these types of pigment dispersions. In the case of the ink application, we saw faster dispersion times, a more stable formulation, and improvements to color and gloss from the AMP-containing ink. In the case of the organic pigments, particularly for our studies with PR122, we saw that you can greatly increase the pigment solids of the paste while reducing the existing dispersant required by about 50%. And so this yields organic pigment paste with smaller and more stable pigment particles. And importantly, we do see a trend towards higher color strength when using the AMP-containing pigment paste to tint a white base paint. So to provide some concluding remarks, pigments can present an array of challenges, largely arising from the need to balance both wet and dry film requirements. And so while there are many formulating tools to control pigment dispersions, an often overlooked solution is the use of amino alcohols. But you need to use an amino alcohol of the right chemistry. And AMP is particularly effective at dispersing pigments due to its specific chemistry that leads to a strong interaction with pigment surfaces. And when you take advantage of that, it creates opportunities to formulate higher performing and more stable coatings, inks, and pigment pastes. So with that, I thank you for your time and attention. Should you have any questions or would like to discuss these results in more detail, I encourage you to reach out to me directly using the contact information provided here. Again, thank you very much for your interest in ANGUS and the work we've just shared.